Definition and fundamental statement of Kirchhoff's current law KCL. KCL says that the algebraic sum of all currents meeting at any node, a point where two or more circuit elements connect, is zero. In plain language, whatever electric charge flows into the node must flow out again. Charge cannot pile up at a point. Think of a busy highway intersection. Cars charge that arrive must leave. The number of cars entering per minute equals the number leaving per minute if no car is parked at the intersection. Sum from k equals 1 to n of I sub k equals 0, where currents entering the node are taken as positive and those leaving as negative, or vice versa, as long as you stay consistent. The law stems from the principle of charge conservation, a fundamental physical law. Mathematical expression of KCL for n-node circuits. For a circuit that has n distinct nodes, KCL can be written as a set of n-1 independent equations. The equation for the reference node is redundant. If we label the node voltages as V1, V2, up to Vn, and the conductance between node I and node J as G sub Ij equals 1 over R sub Ij, the current leaving node I toward node J is G sub Ij times Vi minus Vj. Applying KCL at node I, sum from J equals 1 to n of G sub Ij times Vi minus Vj equals 0, for I equals 1, 2, n minus 1. In matrix form, this becomes YV equals I sub inj, where Y is the nodal admittance matrix, V the column of unknown node voltages, and I sub inj the vector of external current sources injected at each node. This compact representation is the backbone of computer-aided circuit analysis, SPICE, MATLAB, etc. Explanation sign convention for currents in nodal analysis. A consistent sign rule is essential to avoid algebraic errors. The most common convention is: define a positive direction for each branch current, usually away from the node you are writing KCL for. If the chosen direction points away from the node, treat the term as positive in the KCL sum. If the actual current flows toward the node, the term becomes negative because it is opposite to the defined positive direction. Alternatively, you can take all currents entering the node as positive and all leaving as negative. The key is that each branch is counted exactly once, and the signs are applied consistently across all nodes. A handy mental picture is a water pipe junction. If you decide that water flowing out of the junction is positive, then any water that actually flows in must be taken as a negative contribution. When dependent sources are present, the same rule applies. Only the algebraic value of the dependent current, which may be expressed in terms of another voltage or current, matters. Tip: write the KCL equation first with symbolic current directions, then substitute actual current expressions, Ohm's law, source definitions, and finally simplify. This prevents sign mix-ups early on. Find the node voltage VA in the circuit below. A 12-volt battery is connected between node A and ground. From node A, 3 resistors go to ground. R1 equals 2 ohms, R2 equals 3 ohms, and R3 equals 6 ohms. Solution using KCL. Step 1. Choose the ground node as reference, 0 volts. The only unknown is the voltage at node A, which actually equals the source voltage, but we will verify. Step 2. Write KCL at node A. The currents leaving A through each resistor are: I1 equals VA divided by 2, I2 equals VA divided by 3, I3 equals VA divided by 6. Step 3. The battery injects current into the node. If we treat the current supplied by the source as I source entering the node, KCL gives I source minus I1 minus I2 minus I3 equals 0. Step 4. The source current is unknown, but we do not need it because the node voltage is forced by the ideal voltage source. VA equals 12 volts. Step 5. Plugging VA equals 12 into the resistor currents gives I1 equals 6 amperes, I2 equals 4 amperes, I3 equals 2 amperes. Step 6. The source current is therefore I source equals 6 plus 4 plus 2 equals 12 amperes. Takeaway: even in a simple series parallel network, KCL quickly yields relationships between currents and voltages, confirming that the sum of currents leaving a node equals the current entering. Alternative numeric example with different values: node with 2 branches. Node B connects to a 10-volt source, positive side at B, a 5-ohm resistor to ground, and a 10-ohm resistor to node C, which is grounded. Applying KCL at B gives VB divided by 5 plus VB divided by 10 equals I source. Solving for VB equals 10 volts yields I source equals 3 amperes. Problem statement: a planar circuit contains 3 meshes and 4 nodes. The components are R1 equals 4 ohms between nodes 1 to 2, R2 equals 6 ohms between nodes 2 to 3, R3 equals 5 ohms between nodes 3 to 4, R4 equals 10 ohms between nodes 4 to 1. An independent current source I sub S equals 2 amperes entering node 2 from the outside. A voltage source V sub S equals 15 volts between node 1 positive and ground node 4. Goal: find all node voltages using nodal analysis, KCL, and then compute mesh currents. Step 1. Choose reference node. Take node 4 as ground, V4 equals 0. Unknowns are V1, V2, V3. Step 2. Write KCL at each non-reference node. At node 1, open parenthesis V1 minus V2 close parenthesis divided by R1 plus open parenthesis V1 minus V4 close parenthesis divided by R4 equals 0. At node 2, including the external current source entering the node, open parenthesis V2 minus V1 close parenthesis divided by R1 plus open parenthesis V2 minus V3 close parenthesis divided by R2 equals I sub S. At node 3, open parenthesis V3 minus V2 close parenthesis divided by R2 plus open parenthesis V3 minus V4 close parenthesis divided by R3 equals 0. Step 3. Substitute numeric values. Node 1, open parenthesis V1 minus V2 close parenthesis divided by 4 plus open parenthesis V1 minus 0 close parenthesis divided by 10 equals 0, which simplifies to 0.25 times open parenthesis V1 minus V2 close parenthesis plus 0.1 V1 equals 0. Node 2, open parenthesis V2 minus V1 close parenthesis divided by 4 plus open parenthesis V2 minus V3 close parenthesis divided by 6 equals 2. Node 3, open parenthesis V3 minus V2 close parenthesis divided by 6 plus open parenthesis V3 minus 0 close parenthesis divided by 5 equals 0. Step 4. Solve the linear system. After algebra multiplying each equation by the least common multiple to clear fractions, we obtain equation 1, 0.35 V1 minus 0.25 V2 equals 0. Therefore, V1 equals 0.25 divided by 0.35 V2, which is approximately 0.714 V2. Equation 2, negative 0.25 V1 plus open parenthesis 0.25 plus 0.1667 close parenthesis V2 minus 0.1667 V3 equals 2. Equation 3, negative 0.1667 V2 plus open parenthesis 0.1667 plus 0.2 close parenthesis V3 equals 0. Solving gives rounded results. V2 approximately 5.14 volts, V1 approximately 3.67 volts, V3 approximately 4.23 volts. Step 5. Mesh currents using the mesh current method. Define mesh currents IA for the loop 1, 2, 3, 4, IB for the loop 2, 3, and IC for the loop 4, 1. Using Ohm's law across each resistor with the node voltages we just found, compute the branch currents and then relate them to the mesh currents. For example, the current through R1 equals open parenthesis V1 minus V2 close parenthesis divided by R1, which is open parenthesis 3.67 minus 5.14 close parenthesis divided by 4 equals negative 0.37 amperes. The negative sign indicates the current flows opposite to the assumed direction. Continue similarly for the other resistors. The mesh currents are linear combinations of these branch currents. Conclusion: this example shows how KCL provides a systematic way to obtain node voltages, which then feed directly into mesh current calculations. The two methods are interchangeable. KCL is the bridge between them. Circuit description: a circuit has a voltage-controlled current source, VCCS, governed by I sub dep equals 0.1 V sub x, where V sub x is the voltage across a 20 ohm resistor R sub x. The network also includes a 10 ohm resistor R sub 1 in parallel with the VCCS and an independent 5 volt source tied to ground. Goal: find the current through R sub 1. Step 1: label the node where R sub 1, the VCCS, and R sub x meet as node A ground is the reference. Step 2: write KCL at node A: I sub R1 plus I sub dep plus I sub R sub x equals 0, where I sub R1 is V sub A minus 5 over 10, I sub dep is 0.1 V sub x, and I sub R sub x is V sub A over 20. Currents leaving the node are taken as positive. The 5-volt source injects current into the node, hence V sub A minus 5 over 10 is written as leaving the node. Step 3: note that V sub X is exactly the voltage across R sub X. That is V sub X equals V sub A minus 0, which simplifies to V sub A. Step 4: substitute V sub X equals V sub A into the equation. V sub A minus 5 over 10 plus 0.1 V sub A plus V sub A over 20 equals 0. Step 5: multiply by 20 to clear denominators. 2 times open bracket V sub A minus 5 close bracket plus 2 V sub A plus V sub A equals 0. That expands to 2 V sub A minus 10 plus 3 V sub A equals 0. So 5 V sub A equals 10, therefore V sub A equals 2 volts. Step 6: finally, the current through R sub 1 equals V sub A minus 5 over 10, which equals 2 minus 5 over 10, which equals negative 0.3 amperes. The negative sign tells us the actual direction is opposite to the assumed one. Current flows from ground into the node through R sub 1. Key insight: dependent sources are handled exactly like independent ones in KCL. The only extra step is to express the controlling variable, here V sub X, in terms of node voltages or branch currents. This keeps the equations linear or occasionally nonlinear if the dependence is quadratic, and so on. Exam question: in the circuit below, nodes 1 and 2 are connected by an ideal 12-volt voltage source, positive at node 1. The rest of the network consists of resistor 1 equals 4 ohms between node 1 and ground, resistor 2 equals 6 ohms between node 2 and ground, an independent current source of 3 amperes entering node 2 from the left. Find the voltage at node 1, V1, and the current through resistor 1. Solution using supernode technique. Step 1: identify the supernode. The voltage source couples nodes 1 and 2, so they are treated together as a single supernode for Kirchhoff's current law purposes. Step 2: write the voltage constraint imposed by the source. V1 minus V2 equals 12 volts, positive at node 1. Step 3: apply Kirchhoff's current law to the supernode. The sum of all currents leaving both nodes equals 0. Currents leaving the supernode are through resistor 1 and resistor 2. The current source IS enters node 2, so it appears as a negative term. Open parenthesis V1 minus 0 close parenthesis divided by resistor 1 plus open parenthesis V2 minus 0 close parenthesis divided by resistor 2 minus IS equals 0. Substituting values gives V1 over 4 plus V2 over 6 minus 3 equals 0. Step 4: replace V2 using the voltage constraint. V2 equals V1 minus 12. Plug into the KCL equation. V1 over 4 plus open parenthesis V1 minus 12 close parenthesis over 6 equals 3. Step 5: solve for V1. Multiply by 12 to clear denominators. 3V1 plus 2 open parenthesis V1 minus 12 close parenthesis equals 36. That expands to 3V1 plus 2V1 minus 24 equals 36. Combine terms: 5V1 equals 60, therefore V1 equals 12 volts. Consequently, V2 equals V1 minus 12, which is 0 volts. Step 6: current through resistor 1. IR1 equals open parenthesis V1 minus 0 close parenthesis divided by resistor 1, which is 12 over 4, equals 3 amperes, leaving node 1 toward ground. Exam-style takeaway: whenever a voltage source connects two non-reference nodes, form a supernode, write one Kirchhoff's current law equation for the whole group, and add the voltage source equation as an extra constraint. This method avoids having to write KCL at a node where the voltage is undefined due to the ideal source. Forgetting the reference node, do not write a KCL equation for the ground node. Its voltage is fixed at 0 volts and the equation would be redundant. Mixed sign conventions, switching between entering equals positive and leaving equals positive inside the same problem leads to sign errors. Choose one convention and stick to it for the whole circuit. Omitting currents through dependent sources still contribute current terms. Treat them exactly like independent ones. Treating an ideal voltage source as a current path, an ideal voltage source forces a voltage, not a current. You cannot write I equals V over R across it. Use a supernode or write the voltage constraint separately. Double counting a branch. When a branch connects two nodes, include its current only once in each node's KCL equation, once with opposite sign for the second node. Assuming zero current in open circuits, an open circuit carries no current, but you must still include the branch in the nodal diagram. Ignoring it can break the KCL balance. Not converting sources properly. In some problems, you may need to convert a voltage source in series with a resistor to a current source in parallel, the Thevenin or Norton, before writing KCL. Skipping this can make the equations messy. Using wrong units, keep all resistances in ohms, voltages in volts, currents in amperes. Mixing milliohms with ohms without conversion introduces scaling errors. Neglecting nonlinear elements, diodes, transistors, etc. have current-voltage relationships that are not linear. When such elements appear, KCL still holds, but you must use the appropriate nonlinear equation for the branch current. Have I chosen a ground node and excluded it from KCL? Is the sign convention consistent for all branches? Did I write a KCL equation for every non-reference node? Are all source types, independent and dependent, represented as current terms? Have I added extra equations for voltage sources, supernode or branch voltage? Are the units consistent? Have I solved the resulting linear or nonlinear system correctly? Question 1 Electric Circuit Spring 2022 5 marks. A circuit contains 3 nodes A, B, ground. Between A and ground is a 2-ohm resistor. Between B and ground is a 4-ohm resistor. An 8-volt ideal voltage source connects node A positive to node B negative. A 1-amp current source injects current into node A. Find the voltage at node B. A solution. Choose ground as reference V sub G equals 0. Unknowns V sub A and V sub B. Voltage source constraint V sub A minus V sub B equals 8. V sub A equals V sub B plus 8. Write KCL at node A. Currents leaving are positive. V sub A minus 0 divided by 2 minus 1 equals 0. The 1-amp source enters, so it is negative. Substituting V sub A equals V sub B plus 8. V sub B plus 8 divided by 2 equals 1, implies V sub B plus 8 equals 2. Therefore, V sub B equals negative 6 volts. Therefore, node B is at negative 6 volts relative to ground. Node A is then 2 volts, satisfying the 8-volt source. 2 volts minus negative 6 volts equals 8 volts. Question 2 EE101 Final Fall 2021 8 marks. A network has a 10-ohm resistor between nodes 1 and 2, a 5-ohm resistor between node 2 and ground, and a current-controlled voltage source CCVS of value V sub CC equals 2I sub X, where I sub X is the current through the 10-ohm resistor. The CCVS is connected from node 1 to ground positive at node 1. No independent sources are present. Find the node voltages V sub 1 and V sub 2. A solution. Unknowns V sub 1 and V sub 2. The current through the 10-ohm resistor is I sub X equals V sub 1 minus V sub 2 divided by 10. The CCVS imposes a voltage at node 1. V sub 1 equals 2I sub X equals 2 times open parenthesis V sub 1 minus V sub 2 divided by 10 close parenthesis equals V sub 1 minus V sub 2 divided by 5. Multiply both sides by 5. 5 V sub 1 equals V sub 1 minus V sub 2. Therefore, 4 V sub 1 equals negative V sub 2. Thus, V sub 2 equals negative 4 V sub 1. Apply KCL at node 2. Currents leaving are positive. Only 2 branches meet node 2, the 10-ohm resistor to node 1 and the 5-ohm resistor to ground. V sub 2 minus V sub 1 divided by 10 plus V sub 2 divided by 5 equals 0. Substitute V sub 2 equals negative 4 V sub 1. Negative 4 V sub 1 minus V sub 1 divided by 10 plus negative 4 V sub 1 divided by 5 equals 0. Negative 5 V sub 1 divided by 10 minus 4 V sub 1 divided by 5 equals 0. Negative 0.5 V sub 1 minus 0.8 V sub 1 equals 0. Implies negative 1.3 V sub 1 equals 0. Therefore, V sub 1 equals 0 volts. Consequently, V sub 2 equals negative 4 times 0 equals 0 volts. All node voltages are 0. The only consistent solution is the trivial one, meaning the dependent source produces no voltage when there is no independent excitation. Question 3 Power Systems Midterm 2026 marks. 3 branches meet at node X. A 3-amp current source entering the node, a 6-ohm resistor to ground, and a 12-volt voltage source whose positive terminal is at node X. Determine the voltage at node X. A solution. Write KCL. Currents leaving node X are positive. V sub x divided by 6 plus I sub 12 V minus 3 equals 0. The current through the voltage source is unknown, denoted as I sub 12 V. The voltage source forces V sub x equals 12 volts positive at node x. Substitute V sub x equals 12 into KCL 12 divided by 6 plus I sub 12 V minus 3 equals 0. Gives 2 plus I sub 12 V minus 3 equals 0. Therefore I sub 12 V equals 1 ampere leaving the node. Node voltage is simply V sub x equals 12 volts. These three representative problems illustrate the typical exam patterns: a handling voltage source, constraints with supernodes, B dealing with dependent sources, and C mixing current and voltage sources. Mastery of KCL plus the correct auxiliary equations guarantees a full score solution.